You are listening to The Vocal Technologist. Spoken tech for your ears.
Imagine paying $500,000 just for your servers to translate JavaScript into Go.
Right.
Like billions of times over and over again. Sounds like absolute madness, right?
Well, one company was doing exactly that until they fixed it for, I think it was $400.
$400. Which, honestly, that kind of return on investment makes you question absolutely everything you thought you knew about maintaining software architecture.
Oh, completely.
It is a staggering leap in efficiency that forces us to reevaluate how we build these massive systems.
It really is. I am your resident vocal technologist, here to cut through the clutter and figure out what is actually going on. We have pulled together an incredibly dense stack of engineering postmortems, the REST project survey data, and some fascinating research into artificial intelligence agent architecture.
There's heaps of material.
Yeah, heaps. We are going to pull apart the hidden costs of modern web development, exploring how artificial intelligence is acting as both the ultimate cleanup crew and, quite frankly, the biggest mess maker in our code bases. And for you listening, the mission here is to look under the hood. As curious professionals, you want to understand the mechanics of these trends without getting bogged down reading endless technical documentation.
Because somebody has time for that?
Exactly. We're going to break down why things are breaking at scale and, more importantly, exactly how the industry is attempting to fix them.
Let us start with that $500,000 fix, because it perfectly captures this wild era of development we are navigating. This comes from the engineering team at Ricoh.
Right, the Ricoh team.
Yeah, they were dealing with massive compute costs and severe latency issues. Their back-end Go pipeline was calling JavaScript JSON-ATA processes over a remote procedure call, or RPC, for billions of incoming events.
Which is just, to understand why that is so wildly expensive, we have to look at how different programming languages manage memory.
Right.
Go and JavaScript run in entirely different isolated runtime environments. When a Go application needs JavaScript to process some JSON data, it cannot just hand it a lightweight reference to where that data lives in memory.
It has to undergo a massive serialization process.
Precisely.
Meaning it has to take perfectly good structured data in Go, convert it into a flat string of text, send that text across a network boundary via the RPC, and then wait for the node process to wake up.
Yes, and then Node has to parse that text back into an object JavaScript understands.
Right, execute the logic and then do the entire reverse translation to send the answer back.
Doing that billions of times creates an enormous computational bottleneck. The serialization and deserialization cost alone is massive. It burns CPU cycles just translating data back and forth before any actual business logic is even executed.
It is like hiring a highly paid translator to sit between two people who already speak the same language.
That is a great way to put it.
You're paying them a full salary just to write notes back and forth. Then finally you fire the translator, teach one of them a few new words, and just let the two people talk directly. That is exactly what Ricoh did.
They used an agent to rewrite that entire complex JSON-ATA logic into a pure Go implementation.
Which they affectionately called NATA.
Right, nada. And the speed of that rewrite is the critical takeaway here. They accomplished this monumental translation task in just 7 hours.
7 hours.
Yeah, and they spent a mere $400 on API tokens to do the heavy lifting of the logic translation. The result was a 1,000 times speed up on common expressions.
1,000 times faster. And they completely eliminated $500,000 a year in server expenses. It is just a brilliant use of the technology.
It really is.
But we are seeing these massive wins, not just in performance, but in critical security infrastructure.
Yes.
The Lanalam malware incident is a perfect example of this.
Supply chain attacks are notoriously difficult to untangle because they hide within the very dependencies developers trust and install every single day.
You just run npm install or pip install and cross your fingers.
Exactly. In this case, an engineer was simply investigating a frozen laptop.
A frozen laptop. We have all been there, staring at a spinning wheel. But digging into that led them to discover a highly sophisticated attack hidden inside the little Elm init file.
Which is incredibly sneaky.
So sneaky. For anyone unfamiliar, a breathe file in Python is a path configuration file. It is designed to tell Python where to look for modules, but it has a dangerous quirk. It can execute arbitrary code silently the moment the Python environment boots up.
And this malicious script was actively stealing credentials and establishing persistence on the machine.
Right. Normally, defending against that is a grueling manual process. Attackers use automated tools to obfuscate their code, turning it into unreadable gibberish.
Digging through system logs and trying to reverse engineer that payload by hand can take days.
Days of just staring at hex codes. But instead of doing that, the engineer used Claude code.
Yeah.
They fed the system state and the suspicious files.
And the result was instantaneous.
Genuinely blows my mind. It did not just flag the file as bad, it rapidly deobfuscated the script, translating the gibberish back into readable logic.
Wow.
It identified exactly what private data was being exfiltrated to external servers, and it traced the persistence mechanisms through the file system to see exactly how the malware was keeping itself alive.
It really highlights how these models are becoming essential diagnostic tools. When an attacker uses automated tools to deploy malware at scale, defending against it manually is a losing battle.
You are outgunned.
Completely. You need automated intelligence to parse the complexity, highlight the anomalies, and explain the mechanism of the attack instantly.
From the very first symptom of a frozen machine to fully identifying the malware, reporting it to the Python package index security team, contacting the package maintainers, and resolving a massive global security incident. The whole thing took just 72 minutes.
It's 72 minutes.
I spent longer than that trying to center a div on a web page.
It is a phenomenal achievement for security teams.
So artificial intelligence is incredible at untangling deliberate, malicious complexity. It can save a company $500,000 before lunch. But there is a dark side to that speed,
It
right?
absolutely is.
When a tool solves the puzzle for you instantly, you never learn how the puzzle works. And that lack of understanding is exactly why so many developers are begging us to slow the heck down.
That brings us to a philosophy gaining serious traction called code as process.
Code as process.
The core idea is that programming is not just about producing a final text file of code. It is an iterative physical process. When you sit down to write a feature from scratch, you confront intricate details, edge cases, and architectural trade-offs.
Right.
That physical struggle of typing and refactoring sharpens your understanding of the entire system.
Yeah, and when you just prompt an agent to generate a massive block of code, you skip that entire sharpening process. You get the output, but you do not get the context of why the output looks the way it does.
You miss the journey.
Which means you miss the underlying logic.
We are seeing the fallout from this in the open source community. The Rust project conducted a massive survey of their contributors, and the results were quite telling. The project maintainers are becoming completely overwhelmed by an influx of low-quality machine-generated contributions.
People are just blasting out pull requests generated by an agent without actually reviewing the logic themselves.
Exactly. And the problem is that reviewing that generated code is incredibly difficult.
Because it looks right.
Yes. A model can write code that looks syntactically perfect. It uses all the right idioms, the formatting is beautiful, but it completely misses the broader architectural intent of the project.
So it passes the eye test, but fails the logic test.
Precisely. The burden on human maintainers has skyrocketed because the bottleneck in software engineering has fundamentally shifted. It is no longer about the speed of implementation, it is about the accuracy of judgment.
Let me push back on this a bit, though.
Sure.
I hear the code as process argument, but is this not just the old guard whinging about calculators?
That is a common argument.
People complained when we got advanced autocomplete, too. They said it would make us lazy and ruin our ability to write pure logic. Is delegating to an agent not just the next evolution of tooling?
That is a very fair comparison on the surface. However, delegating architectural logic is fundamentally different from autocomplete.
How so?
Autocomplete finishes your thought based on what you have already typed. An agent often invents the thought entirely from scratch. And when you scale that up across an entire industry, you encounter a systemic risk called model collapse.
Oh, model collapse. I was reading through the research on this, and it is a terrifying concept.
It really is.
The way I understand it, it is essentially digital inbreeding. If these massive language models keep training on data that was generated by previous iterations of language models, the output gets mutated and homogenized. Am I understanding the mechanism correctly?
You have grasped the core mechanism perfectly. Model collapse happens when models begin to degrade over successive generations because they are starved of unique human-generated data.
Like making a photocopy of a photocopy of a photocopy.
Spot on. The rare, diverse, eccentric patterns of human thought get smoothed out. You lose variance. If we rely entirely on these tools to write our code bases, those code bases will eventually converge into a homogenized, brittle state that lacks any creative problem solving.
It is like taking a helicopter to the top of a mountain.
Okay, I like that.
Sure, you reach the peak instantly, which feels amazing. But your muscles have not adapted. You do not know the terrain. You have absolutely no idea how to climb.
Right.
And the second the weather turns bad or a weird bug appears in production, you are completely stuck because you never learned the mechanics of the mountain in the first place.
That mountain analogy is spot on. And when the weather turns bad in software, it usually means unraveling massive architectural bloat that no one on the team truly understands.
Skipping that deep understanding inevitably leads to massive bloat. But we cannot just point the finger at artificial intelligence for this. Humans are perfectly capable of creating absolute disasters all on their own when they overcomplicate architectures.
We certainly are.
Look at the absolute state of what happened at Dropbox.
The Dropbox monorepo is a classic example of human-engineered bloat. They had a single code repository that had ballooned to an astonishing 87 gigabytes.
87 gigabytes for a code repository. Just cloning that codebase to a new machine took over an hour. Imagine being a new developer showing up on your first day and you spend your entire morning just staring at a progress bar waiting to download text files.
It is entirely unproductive. But the root cause was not some massive machine learning data set hidden in the files. It was a failure to understand the mechanics of Git delta compression.
Right.
Git is designed to be highly efficient by storing the differences, or deltas, between file versions. If you have a massive text file and you change one word, Git does not save a brand new copy of the entire file. It just saves a tiny record saying what changed.
But Dropbox discovered that their basic translation files were completely bypassing this compression.
Yes.
Because of how these language files were automatically formatted and updated by their internal software, the underlying structure of the text shifted dramatically with every minor update. To Git, it looked like an entirely new file every single time.
So it was storing massive redundant copies of these files over and over again, severely bloating the pack files.
Their fix was remarkably straightforward once they actually understood the mechanics of the tool they were using. They performed a tuned server-side repack,
Which is a very specific Git operation.
They essentially forced Git to recalculate and optimize those deltas using custom parameters tailored to their specific file structures. And just like that, clone times dropped from over an hour to under 15 minutes. The repository shrank from 87 gigabytes down to 20 gigabytes.
It shows why deeply understanding the underlying toolchain is critical. If you just accept the bloat as a necessary evil of a large project, you waste thousands of developer hours.
And we see this exact same lack of understanding causing massive performance issues at the architectural boundary as well. The OpenUI team fell into a trap that I think a lot of incredibly clever engineers fall into.
Oh, the WebAssembly issue.
Yeah, they wanted their web parser to be blazingly fast, so they wrote it in Rust and compiled it to WebAssembly.
Which, on paper, sounds like the optimal engineering decision. Rust is incredibly performant, memory safe, and designed for heavy lifting.
But they hit the WebAssembly boundary tax.
This is a crucial mechanic to understand if you are building modern web applications. WebAssembly runs in a separate, isolated memory space from JavaScript.
So they do not just share a brain.
Exactly. So when your JavaScript frontend needs to send a large string of text to your WebAssembly parser, it cannot just pass a lightweight memory reference. It has to serialize the data, copy it byte by byte across the boundary into the isolated memory, parse it, and then copy the entire result back out to JavaScript.
That copying overhead completely erased the performance gains of using Rust. They literally had to throw the Rust code away and rewrite the entire parser in TypeScript.
Because TypeScript runs in the exact same engine memory space as the front end, there is absolutely no boundary tax.
To make it fast enough, they implemented an ON statement-level incremental caching system.
Going from an ON squared reparsing approach to an ON approach is a massive fundamental shift in how the application scales.
Let me translate that big O notation for anyone who does not dream in computer science algorithms.
Please do.
Think of an ON squared approach, like having to reread an entire massive book from chapter 1 every single time you edit a single comma. It gets exponentially slower the bigger the book gets.
That is a painful way to read a book.
Very painful. Instead, they built a caching system that only reads the specific sentence that was edited. It scales perfectly no matter how massive the application becomes. They achieved instantaneous streaming performance just by staying within the JavaScript ecosystem and understanding the mechanics of their memory boundaries.
It is a brilliant example of prioritizing systemic empathy over pure component speed. You have to understand how the pieces talk to each other across boundaries, not just how fast a single piece runs in isolation.
Systemic empathy, I like that.
Mhm.
Sometimes, though, the bloat is just downright comical. Let me mention the Fieldy app.
Oh, the wearable app.
Yeah, is a wearable application. They managed to cut their total app size by 25%. Do you know how? By simply deleting an 18 megabyte bundled font file and some bloated calendar libraries they were not even actively using.
It is staggering how quickly unused dependencies can accumulate when developers stop paying attention to the final build size of their artifacts.
We are building enterprise models and running full 3D engines natively in the browser, but our applications are crashing because someone left an 18 megabyte font file in the build folder, which, yeah, is exactly as terrifying as it sounds.
It proves that rigorous engineering discipline is still required, regardless of how advanced our automated tooling becomes.
This brings us to the ultimate question of this whole exploration. If humans naturally create bloated architecture by ignoring compression and bolting on massive font files, and artificial intelligence creates fast but brittle code because it lacks context, how do we combine them without everything catching fire?
We clearly have to build entirely new rules of engagement.
We absolutely do. The industry is moving from simply writing code to orchestrating complex automated systems. A prime example of this is Anthropic and their new harness design for long-running application development.
They recognized early on that models suffer from a severe limitation they call context anxiety.
Context anxiety. The research papers call it the lost in the middle problem.
Exactly.
It is like asking someone to memorize a massive grocery list, dropping them at the store, and making them shop for 3 hours. By the time they hit the checkout, their brain is so overwhelmed by the middle of the trip that they completely forget what was at the top of the list.
That is a perfect visualization. When an agent is given a massive, unstructured coding task, it loses the plot. It forgets its initial instructions or gets stuck in an infinite, repetitive loop.
To fix this, Anthropic completely abandoned the idea of a single, omnipotent agent doing all the work. Instead, they implemented a multi-agent architecture. Specifically, they use a GAN-inspired approach, which stands for Generative Adversarial Network.
Right.
So instead of one worker, you have a master art forger and a world-class art detective locking horns in a room.
That is exactly how it works. One agent acts as the generator, writing the code and attacking the task. A separate, completely independent agent acts as the evaluator, equipped with very explicit, structured grading criteria.
So it is just looking over its shoulder the whole time.
The evaluator constantly checks the generator against these criteria, providing contextual handoffs and corrections. It is a robust system of checks and balances that physically stops the generator from hallucinating or forgetting its instructions during long-running tasks.
And the structural shift is completely changing the engineering job market. The traditional role of the data scientist is practically unrecognizable now. We're not sitting around training foundation models from scratch anymore. The massive models are already built by the tech giants.
The new mandate for a data scientist or an engineering lead is to own the evaluation infrastructure. Their primary job is to keep automated behavior measurable and strictly improvable.
They do this by building complex error taxonomies from production traces. You take an error taxonomy, which is essentially a detailed catalog of every stupid mistake this system has made in the wild, and you turn that catalog into a deterministic schema check.
Yes. Before the generating agent is allowed to commit any code, the evaluating infrastructure physically blocks the deployment and runs the new code against the catalog.
If it spots a hallucinated variable or a missed error handler, it rejects the code and forces the generator to try again.
The focus is entirely on evaluation. You have to ensure that when a system generates an output, it perfectly matches the expected structure before it ever reaches production.
And this level of strict governance extends to the developers writing the code alongside the automation as well. We are seeing platforms like Stack Overflow pushing hard for explicit coding guidelines specifically designed for automated agents.
Because if you just let 5 different agents loose in your enterprise repository, they will all invent their own naming conventions, their own folder structures, and their own error handling protocols.
It would be absolute chaos within a week.
It would be entirely unmaintainable. These guidelines have to be fiercely prescriptive. You have to lay down the absolute ground rules for the tech stack, the exact methodology for layout, and specifically how errors must be bubbled up to the user.
You are essentially writing a strict constitution for your automated workforce.
Which brings it all together beautifully. The job is no longer just writing the code. The job is managing the system that writes the code.
You are transitioning from being a bricklayer, placing individual bricks perfectly, to an urban planner. You have to design the streets, set the zoning laws, and make sure the plumbing works across the entire city.
Because if you do not build the infrastructure for evaluation, the automation will build a sprawling, terrifying city that no human can possibly navigate.
That is the crucial reality we all have to navigate moving forward. The infrastructure of evaluation is more important than the speed of generation.
Absolutely.
It makes you wonder. So the next time you let an agent write a massive chunk of logic for you, ask yourself, are you actually saving time, or are you just borrowing it from the future maintainer who has to unravel it tomorrow? Keep questioning the tools you use every day, and as always, your vocal technologist will catch you next time.
Spoken Tech for your ears.